Okay. So let's start. So welcome to my second lecture in this series, and so I will continue with what I started yesterday. So yesterday I introduced the model of bounded workspace algorithms, and I gave some overview of related models and some philosophical aspects of the model. And we ended with, so after the model was clear, we ended with one very simple problem. So the first problem you always consider when doing computational geometry. And we convinced ourselves that also this problem has some relatively simple solution in the bounded workspace model. And so today I wanted to look at some other basic problems from computational geometry, 3 or 4, depending on how much time we have. And I wanted to show you how these simple problems can be solved in bounded workspace. And for 2 of them, I think we have some relatively satisfactory solutions. The third one is a bit more tricky, and so I'm not sure if this is actually the optimal solution. But already this solution, it requires some geometric intuition that's more advanced. Well, maybe not too advanced, but at least some knowledge. So let's see. What do we start with? So after we can do, so yesterday I showed that we can do convex hulls in quadratic time and constant space. And so the next thing after convex hulls you always look at is triangulations. And of course there are different triangulations. And so what is it? So I guess everybody knows. So we are given some points at P, P1, P2, Pn, and recall that I'm in the constant workspace model. So this is given in some read-only memory and in arbitrary order. So I cannot assume anything about how these points are arranged. I just know that there exists some array which stores these endpoints in some order, and I also assume a general position, whatever this means. In arbitrary order. And what we want is, so first I will consider the case that we just want some triangulation of P, and then next I will look at the case that we want some special triangulation of P, and of course the most special triangulation is the Delaunay triangulation. But so first let's do the simple algorithm, the more simpler problem where we just want. Thank you. First I look at the simpler problem where I just want some triangulation. So, that's much better. Some triangulation of P. And so everybody knows what a triangulation is, yes? So this. So here's some point set, and here's a triangulation of this point set. And again, I have to say, since I'm in, so what exactly do I mean by this? Since I don't really, so usually in your computational geometry class, when you compute a triangulation, then it means that you compute some data structure which represents the plane graph which is this triangulation. Since I'm in the bounded workspace world, I'm not really allowed to store a data structure. So I cannot have some DCEL or some other structure to represent it. So what do I want? So what I want is I want to output the triangles of this triangulation in any order. So it's relatively, I mean, you might imagine other things, but so the simplest problem would be that you just want some algorithm that uses constant space and that outputs the triangles of this triangulation in some order. So just triples of points, and you want to have the guarantee that these triples of points, they represent the triangles of a consistent triangulation of the point set. So this means, so i.e. triangles in some order. And also I want that no triangle is output twice. So I don't want to have redundancy. So I want, and so the algorithm is supposed to write all the triangles of the triangulation in some order such that every triangle appears exactly once. Okay. And as you may know, so if you have a point set there, if you have a planar point set, there exist many different ways of triangulating it. So there can be exponentially many, or I guess usually there's an exponential number of ways how you can triangulate the planar point set. And so this means we have a lot of choices. So we have a lot of freedom in solving this problem. And since we're in the constant workspace world, I want to pick some triangulation which is easy to handle with constant workspace. So I want some triangulation which is somehow locally defined. So we have many choices, and the idea is since we have a lot of freedom in choosing our triangulation, is so output a triangulation that is easy to handle local with constant workspace. Yes, so that's the idea. So now I need to tell you what particular triangulation I want to look at, so how it's supposed to work, and how we will represent this with constant workspace. Yes, but everybody clear on what the problem is, or any questions so far? But I guess we all know the definitions. Yes? So let's see. So how can I given some point set, how can I find some canonical way of triangulating it such that I can easily handle this triangulation with constant workspace? And so I guess there's some very easy way of triangulating a point set, so if you don't really care about any properties. And so also I somehow want to use some of the things that we learned yesterday. So yesterday we learned that it's easy to compute convex heights. And so I want to build on this. And so one way to triangulate this point set, which is useful, is this. So you do it incrementally. So you go from, so you go in one direction through the point set, like this. And then you greedily add the triangles. So like this. So I start, and the first 3 points, I don't have a choice. They make a triangle. And then, as I continue, every time the next point comes, as I go through the points from left to right, I add all the triangles, the maximum number of triangles that I can add to increase my triangulation. So this point comes, I add this triangle. So this point comes, I can add 2 triangles, this one and this one. Then this point comes, I can add again 2 triangles. This point comes, I add 1 triangle. This point comes, I add 1 triangle, 1 triangle, 2 triangles, 1 triangle. And here I have, I think, I'm not sure, depending on how exactly it goes, so maybe even 4 triangles. Yes? And so this is how I want to define my triangulation. So the triangulation is defined in such a way that I go through my points from left to right, and every time a new point comes, I add the maximum number of triangles that I can add. Yes? And so let's write this down. So the rough algorithm goes like this. Rough algorithm. So process points P in X order, and when processing P in P, add maximum number of triangles going to the left from P. Okay, and so this is what I want to do, and now I need to think about how I can implement this strategy with constant workspace. And so the first thing is, so I need to be able to process the points in X order. So I said I'm given the input in read-only memory, and I cannot make any assumptions about the point sets, but I have some, and about the order in which it is given, but I have some general position assumption. And so in order to process the points in X order, I think it's very easy, right, so that you can always find the next point. So you know what the last point is that you had, and then you just scan over the points that you can find the next point that you want to process in linear time, right? So we can do this, so we can find the point, find next point in O of n time, right? That's clear to everyone, right? Or is this not clear? No. Well, it's very, very easy. Okay, now this is the more difficult part. So how do I do this? So now here I have my new point P, and I want to add all the triangles. Okay. So and here are some other points. And I want to add all the possible triangles which go from P to the left. And so what are these? So all the possible triangles which are consistent with what I did before. And so how can I find these triangles? What are these? So that's now what I need to think about. So what are these triangles? Where do they come from? How can I find them? So where would these triangles go? So these triangles would be this triangle, this triangle, this triangle, and this triangle. Yes. So how would you characterize these triangles? Or did I? Exactly. So it's a convex hull. So what I need to do is I compute the convex hull of the point set to the left, and then I add the triangles to all the edges which P can see. Good. So that's good. And then the next thing is, so I cannot really add the compute the convex hull of the point. And so this is good because yesterday we found out that it's easy to compute the convex hull of a point set. So we know how to do this. So that's good. So we can use something that we know. And but so of course there's one little complication. So because you cannot really compute the whole convex hull, because so if there's many points here up here on the convex hull, you would be computing them again and again and again. So this is very inefficient. So you actually just want to compute the convex hull of the part of the convex hull which is visible from P, right? But so this again is not difficult to do because what do we know? So we know where to start. So we certainly know one edge always because we know there has to be one edge from P to the predecessor of P in X order. So this edge will be here. So we know we certainly have to start here, and we cannot make a mistake by this. So and we know this point because we just processed it in the previous iteration, right? So this is good. And then so we have the rightmost point where we can start, and we also know how we can just build the part of the convex hull that is important to us. Because if you remember the algorithm for a convex hull that we had yesterday, it was just gift wrapping, and gift wrapping has the great advantage that it creates the convex hull one by one, right? So I can really generate all these edges one by one, and I can stop once I do not need any more additional edges, and it will not cause any additional cost, right? And so this is good. So we are very lucky that the algorithm that we had yesterday it exactly gives us what we want. So what do we want? So create triangles between P and the convex hull edges visible from P. Right, so this is how we design the triangles. So we design the triangulation. We add triangles between P and the convex hull edges to the left of P, and we find these convex hull edges. So find the convex hull edges by gift wrapping because I know I can start from the predecessor of P, starting from P's predecessor. Yes? So that's it. So, and then every time we find a triangle, we output it. So we do this gift wrapping, and every time we find a new edge, we make a triangle between P and this edge, and we output this triangle to our write-out memory, and this gives us the guarantee that we output all the triangles of the triangulation. Yes, so this is the algorithm, and yeah, is there any question about this? Yes, but only the part which is visible from P, not the whole convex hull, but only this part. The horizon, yes. And so now, of course, the question is, so there's some worries that you have. So how long does this take? So now we need to analyze it. But so before we analyze the running time, so you all believe that this somehow works, and this is an easy idea to implement, yes? Okay, so that's an easy algorithm. And now we need to analyze it. And so I already started a little bit with the analysis. So I said, so the first part, so processing the points in X order, it just takes linear time per point. So this is easy. And so now we need to analyze this part. And so here we have to create these triangles. We have to create these triangles, and we have to do the gift wrapping. And as you may, or the first worry might be, of course, that this may take a long time, right? So you have one point P, and there are a lot of points like this, right? And so I have to add a lot of triangles. And I will be very busy, right? And so it may take a long time, right? And but can we still something intelligent about this? So first of all, maybe before we think about this, I mean, the problem will go away very easily, I promise you. But so before we think about this, so how long does it take to output one triangle? So what can we say here? So we know for every triangle that we output, we have to perform one gift wrapping step, right? So every time we find a new edge of the convex hull, we also output a triangle, right? So this means it takes, so this step it takes linear time for each triangle, right? So each step is O of n time. So where by a step I mean so each edge, right? So every time I discover a new edge of the convex hull, it takes me linear time, but then I also output a triangle, right?
Sorry.
Yes?
For gift wrapping, you have to omit the points after predecessor. But for that, you have to save the node, save the points before the predecessor. But you cannot save it.
Okay, so yes. So good point. So I was, so that's one detail which I omitted. So I don't really do a gift wrapping on the whole point set. But so I have to be a bit careful, right? So when I do the gift wrapping, I have to put some filter into my algorithm, right? So I know P, right? So I know the x coordinate of P, and I have my point in the I have my point set P here in this input array. And so now when I do some gift wrapping, I know the predecessor of P, and I want to use my convex hull algorithm here on the point set. But I cannot really use the whole input because, as you pointed out, there's also points which are to the right of P. So when I go through my input, I need to have some test before I look at the point whether the x coordinate of the point is less than the x coordinate of P or larger, right? So, but this is easy because so here I write O of n time, right? So this is why I'm writing each step it takes O of n time. So it's the whole point set. I have to look at all the points, but for the algorithm, so if a point lies to the right of P, I just pretend it's not there. But it gets counted here in the running time. Yes. Okay, yes, good point. So we have this, and we know each step takes O of n time. So each triangle, right? And so this now is some very easy instance of amortized analysis, right? So now you see what happens, or can you guess what the running time will be? No, n squared. Exactly. So why is the running time n squared? Because, so first of all, I need to process the points in x order. So every time so there are n points, and finding the next point always takes n times. So we have a quadratic time for this step. And then here, we don't know. I mean, for one point, we may spend a linear or a long time. But we know that overall, every time we spend linear time here in this step, we output a triangle. And we know that the triangulation has a linear number of triangles. So at most 3n. Or 3n minus 6, something like this. And, oh no, is that the oh sorry, that's the number of edges. The number of triangles is 2n minus 4. So at least a linear number of triangles. if I'm correct. I'm not sure. So we have a linear number of triangles, and so for every triangle we need linear time. So this means the total amount for these steps is also quadratic. So we can find the triangulation in quadratic time and constant space. O of n squared time, O of 1 space. Yes? And yeah, that's it. And I mean,
Sorry,
yeah. The passes, so I think you also need n passes because so every time you find the next point, that's one pass.
Every time you should pass all data to find just one next.
Yes.
One next.
Yes. So this is n passes. So I think this one takes one pass, and that one takes one pass for every triangle. So it's something maybe like 5n passes. So at least linear. Okay. Yes. So any questions about this? So this is also, and so again, so this is a kind of result we're happy with because it matches the time that we needed for convex hires. So so finding the triangulation is not much more difficult than finding the convex hire. And at least in this case, if we know the edges of the triangulation, we can also identify, I think, the edges of the convex. I'm not sure if that's so clear in this model, but at least the way this algorithm works, you would. Again, not so clear. But I mean, at least, so it's not clear that, okay, so at least, so in this model, it's not really clear to me if the triangulation problem and the convex hire problem are related to each other as they are in the usual model, but at least still we would expect that this running time is pretty good or maybe optimal, but the usual argument that we give that computing a triangulation cannot be easier than computing a convex hire because the convex hire is part of the triangulation. I'm not really sure if this applies in this case. So I cannot say that this is optimal because I haven't thought about it hard enough. Okay. Yes? Any more questions? Or this is okay. So this is the first one, then the second one. Is now I know how to compute some triangulation, but now I want to have a special triangulation. Now I want to find the Delaunay triangulation, right? And so everybody knows what the Delaunay triangulation is. So Delaunay. And okay, so it's again the same situation. So we have the point set given in some order, and we want to output the triangles of the Delaunay triangulation in some order. And so I think everybody could find a very simple algorithm. So what's the first algorithm you would try for? So I would say that everybody here should be able to find an algorithm that outputs all the triangles of the Delaunay triangulation in time n to the 4. Exactly. So the very easy algorithm, so I mean, or let's even write trivial. So if you know the definition of the Delaunay triangulation, you can immediately do n to the 4 time in O of 1 space. Right? Because all you need to do is you need to enumerate all possible triples in the point set, and there's n cube of them, and for each triple you need to check whether this triple is the triangle in the Delaunay triangulation. And then this you can do in linear time by just looking at all the points and checking whether there exists one point which lies inside the circumcircle of this triangle. If there is such a point, it's not a Delaunay triangle. If there's no such point, then it is a Delaunay triangle, and you output it. So this everybody can do. This is somehow, so this is the baseline. So we need to do something which is faster than n to the 4. And now let's see. How can we do something faster? And so I will show you how to improve this to how to get this down to n squared. So it's actually not more difficult to compute the Delaunay triangulation than to compute some arbitrary triangulation. And so what is the idea? So how does it work? So the idea is that now we look at any point for P in P, for every point. So we go through all the points and we output the incident triangles in clockwise order. So my strategy is, what I'm going to do is I'm going to describe to you some procedure so that you give me some point P, and I will then explain to you how it is possible, starting from P, how you can enumerate all the triangles which are incident to P. So I guess this is called the star of P. So I will show you some method which so you have a point P and you just I give you some way of how you can enumerate all these triangles which are incident to P one after the other until you went in one circle, and then you have all the triangles which are incident to P. You check all the points, so you repeat this for all the points, and then you may see every triangle, some triangles more often. Yeah, 3 times. But then you have to do some tie breaking when you output the triangle, that you output each triangle at most once. But so that's easy. Okay. And so, right, so the strategy is, so we have some point P and we want to enumerate all the triangles which are incident to P in clockwise order. Oh, now I drew it counterclockwise. So that's right, counterclockwise. Counterclockwise. Okay. And so the first question is where to start. So how do you start? So I have this point P, and I want to find all the triangles of the Delaunay triangulation which are incident to P. But I only know P. I don't know and I need to find some first triangle where I can start. So how can I find some initial triangle where I can begin with my search? So do you know? So is there some natural thing? So how do I know? Is there some triangle or at least some edge incident to P where I can be certain it has to be there? The first point in first point, I'm not sure. The first point after. I'm not sure. So it might be like this, right? And then maybe like that. So it doesn't have to be so. But it's almost like this. So it's not the first point, but it's the nearest neighbor of P, right? So. So we know, so if you know something about the Delaunay triangulation, you know for every point its nearest neighbor, so there has to be an edge between the point and its nearest neighbor. And the nearest neighbor is the other point which has the minimum distance into P. So we know that we start with nearest neighbor of P. Start with nearest neighbor of P. Right? So we have P. And what we do is we go through all the other points, we compute the distance to P. So here are all the other points. We compute the distance to P for all the other points, and we find the one which is the nearest neighbor, and we know we have to start here. Yes? So we know we can start here, this is safe. Okay, and so this takes O of n time. Okay. And the next thing is, so now I have an edge where I can start. So here I have P and I have its nearest neighbor. So let me call it Q. So here's the nearest neighbor. And so now I know this edge. And now I need to find a triangle, right? So like this. So now I want to find a triangle here. Maybe this one. So there will be this the Delaunay triangle, which is incident to this edge and which lies counterclockwise to it. So how do I find this? And now the idea is, so I look at this edge. So I know the triangle, it has to be above this edge. So I can look at this line, right? So I extend this edge to a line, and I know that all the points that I need, it's so all the points that I need, they lie here. But there may be many points. And so now how do I do it? So, well, there's not so much I can do. I can just, okay, so here's another point. So now what I do some kind of greedy algorithm. And so I know that there are all the points that are here, so the points that are they're not important, but I don't know which one to take. So, well, I don't know which one to take, so let me just try one. So let's say this one here. So let's say this is the first point, and so I try this point and I make a triangle here. Right? And so I make this triangle, and then the question is this triangle good or not? Well, it's not. Well, obviously not, because there's this point in here. But so how can I see if it's good or not? So I look at the circle and I see whether it contains another point. And if it does contain another point, what do? I kick this point out, and I replace it by that one. Right? So you all understood what just happened. So I have this triangle here, and I check whether the circle here is empty. If it's empty, then I know it is a Delaunay triangle. If it is not empty, then I can replace it by that point here. And then I have another candidate, and again I check, and I continue. Yes? But this is still not good enough. I mean, this takes too long. And my claim is you can even do it more easily. You can just do it in one sweep. So I don't have to check every time all the points. So I just go through the sweep. I just go. So I know the points, they are stored in my array in some order. And what I do is I just go through the points in the order in which they are stored in the input, which I don't know what it is. And I take the first point, which lies to the left of this line. I make a triangle with this point. Then I take the next point, which lies to the left of the line. I check whether this point lies inside the circle. If it does, then I replace my current point by this point. If it does not, I just ignore it. And I continue, and in the end, I'm left with some point. And my claim is that this point will be the Delaunay triangle. Yes? Yes?
Is it possible that the point that we have passed from lies inside the circle in this new triangle?
Yeah, so this is the question, right? So can this happen, right? So does it work, right? So you're worried that, I mean, I go from left to right. Now every time I find a new point, I kick it. So every time, I have my current candidate, and every time I find somebody who invalidates this current candidate, I put a point in there. And if I don't find somebody, I keep this and make this my Delaunay triangle. And the question is, does this work? So, or can something go wrong? And so what's the way to think of this? Think about this to make sure that there's no mistake. So how do we analyze it? So, okay, but maybe first let me write this down. So start with NMP. So to continue CCW, perform a greedy algorithm. And so what do we do? So we have current edge PQ. So I'm just summarizing what I just explained. So we want to continue. So we have some edge PQ of the Delaunay triangulation, and I want to find the next edge. So I want to find the triangle which is to the left of this edge. And so we do a greedy algorithm. So we have a current edge PQ, and we always have a candidate point R, which is left of the line through PQ. So in each step, so I have this current edge PQ, and I have some candidate point which I call R, which lies to the left of this line. What I do is, so I take the next point to the left of this line. So next point R prime, left of PQ, And so this is, let me make this a bit cleaner. So this is the current situation. I have my candidate point R, and I have my current triangle. And then I take the next point R prime. And now there's two things that can happen. So either this point, or R bar, either this point R bar can lie inside the circumcircle or outside the circumcircle of this candidate triangle. If it's inside the circumcircle, I replace R by R prime. If it's outside the circumcircle, I continue. Yeah? If R prime in the circumcircle PQR, we make R prime, R bar our candidate, else continue. Right? And that's the algorithm. And now the question is, does this work? Or can I make a mistake like this? And okay. And now let me argue why this works. Or any questions so far? Everybody understand? It's very simple, yes? Okay. And so now why does this work? So first of all, so what I know is PQ. So what I know is PQ is an edge of the Delaunay triangulation. So I have to guarantee that this edge that I'm looking at, so by induction, I have to guarantee that the edge I'm looking at currently is a valid edge of the Delaunay triangulation. So there has to be, well, I mean, it may be the case that PQ is part of the convex hull, but let's assume it lies inside the triangle. So let's assume that PQ lies inside the triangulation. Then I have to guarantee that PQ is an edge of the Delaunay triangulation. So there has to be a triangle that is incident. So there has to be something here. So there has to be one candidate, right? And I know, because there exists one candidate, so I know that there exists a solution. I know that as soon as I found the right candidate, so as soon as R has become the right candidate, it will not be invalidated again, right? Because I know that there exists a point such that the circle PQR is empty. And as soon as I found this point, nothing will happen anymore. I will output it, right? So as soon as I make this point my candidate, I will output it. Yes? So if ever the right third vertex of the triangle becomes the candidate, it will be output. Yes? So, and I will also consider this point, right? So the only thing which can go wrong is that I have some current candidate point, and I see the true point, but for some reason I do not pick the true point. So the true point will not be in the circumcircle. This is the only thing that can go wrong right now. Yes? So far? Clear so far? So the only problem that can be is that for some reason, I do not execute this for the candidate. Everything else, once I do this, I'm fine. And now I just need to argue that when I look at the true answer, I will find it. But when I look at the true answer, that I will find it, this is also clear, because I just need to look at 4 points. I need to look at the point P, Q, the true candidate, and the point which is which happens to be my current candidate. And if I look at the Delaunay triangulation of these 4 points, then PQ and my true candidate will make a triangle. This is because so Delaunay triangulations are monotone. So if there's a point, so if PQR is a triangle in the Delaunay triangulation of P, then PQR will be a triangle in every subset of P which contains PQR. This follows immediately from the empty circle property, right? And so this means it cannot be that I look at my true candidate and I will not find it. I will not take it. Yes, because of the hereditary property, whatever my current candidate is, it has to be kicked out by the true candidate, because the true candidate will make a triangle with PQR in the Delaunay triangulation of these 4 points. So there has to be a conflict between the current candidate and the true candidate. Yes? And so this is why the algorithm works. Yes?
is no point over that line.
Good point. Yeah, so this I just briefly addressed, but so this is a good question. So I cheated you a bit because I drew these points here. There may be no candidate at all, right? So that's one problem that may happen. But otherwise, you believe me, if there are points, if there's at least one point up here, I'm fine. I will find my triangle. Yes, you all believe this? Okay. So now the next question was, so what happens if there's no point? Exactly. So what does it mean? So what does it mean if there's no point up above here, above this edge? What do we know then about this edge? We know this edge will be part of the convex hull. And then we can just do gift wrapping. So if we're in this situation that, so here we have P and Q, and there's nobody here, so this is all empty, then I can just do gift wrapping like this, and so I find the first, so I just continue like this, and I find the first point which I hit when I rotate this line. And this becomes my next edge, and I know this will also be an edge of the Delaunay triangulation because it's an edge of the convex hull. Yes? Okay. And so how long does this take? So this takes linear time, right? So this takes O of n time. So what does it mean? So this means we can output all the triangles of the Delaunay triangulation in linear time, or even more precisely, for every point P, I can enumerate all the incident edges in clockwise order in linear time per edge. Yes? And this will be important in just a minute. So the conclusion of all the things that we talked about here, so this is the conclusion. So for each P in P can enumerate we can enumerate incident edges of DTP in O of n time per edge.
You use O of n just for one triangle?
Yes. For each edge, O of n time. But so in clockwise order, in counterclockwise order. Good. And so again, so we know, so we need linear time per edge, and the triangulation only has a linear number of edges, so we again get, by the same argument, O of n squared time O of 1 space. Yes? Everything clear so far? Okay. So this is good. So we're making good progress. So we've solved all our problems so far. And so these are also solutions we can be, I think, satisfied with, because somehow it seems that n squared is some natural bound for constant workspace algorithms. So it's very rare that you can do faster. Now let's look at the next problem, and the next problem gets more tricky. So now it becomes maybe interesting. So we have Delaunay triangulation, some triangulation, and now what do we do next? The next thing will be the Euclidean minimum spanning tree, Euclidean MST. So how can I find the Euclidean MST of a point set? So we have P R squared, find MST of P. And so at first it looks easy, right? So because we were just very successful in finding the Delaunay triangulation, right? So we know we can find all the edges of the Delaunay triangulation in linear time per edge. And we know that the Euclidean MST is a subgraph of the Delaunay triangulation. So we know the minimum spanning tree of the Delaunay triangulation is the Euclidean minimum spanning tree. Yes. So we just need to. So what is it? So we know how to find all these edges. but we just need to find the minimum spanning tree. And so this is where the problem begins. Because now we cannot store these edges. So we can enumerate the edges, but we can just, at each step, we can only look at a constant number of edges. So we cannot really store the whole thing, and we can, so it's not really clear how to use any of the standard minimum spanning tree algorithms. So what will we do? I mean, it's not clear what you, so Krusk's algorithm won't work, Podrufka's algorithm won't work, Prim's algorithms won't work. No MST algorithms work because you cannot store the MST. So, but still, let's see if we can implement the strategy. So the strategy is, so enumerate all edges of DTP and output edges of EMST of P. So what we want to do is we want to find all the edges of the Delaunay triangulation. We know how to do this. So we just run our Delaunay algorithm, and every time this Delaunay algorithm outputs one edge. So there's another strategy of designing a constant workspace algorithm. So we can somehow put them one after the other, right? Because they always have a constant workspace. You can, so the output of one of them you can use as input for the other one, sometimes. And so this is what we want to do here. So we enumerate all the edges. We know how to do this. We just saw this. And now for each edge, we want to check whether it's an edge of the Euclidean minimum spanning tree. And this is the main question. So how can we check whether this edge is an edge of the EMST? So how to, so we have this. So let E be an edge of Delaunay triangulation of P is E, so how to check if E is an EMST of P. This is the question now. So this is the next thing we need to see. And so, yes. And so now let me, oh, I see. So I don't have that much time to get back on schedule. So here you have your edge PQ. So we know this one. And we want to check whether it's part of the Euclidean minimum spanning tree or not. And so what's the and so we need some criterion. We need to know what do we need to check in order to see whether this edge is part of this or is part of the EMST or not. And and this criterion, ideally, it should be possible for us to check it with constant space. And so first of all, there is one simple test. So how can you test whether an edge belongs to the Euclidean minimum, to any minimum spanning tree, not just, so you're given some weighted graph. How can you test whether an edge belongs to the spanning tree?
You should use a cut.
Exactly.
Minimum should be a minimum edge that crosses the cut.
Exactly. So, so what we know about minimum spanning tree edges is the cut property. And the cut property is, so an edge is part of the minimum spanning tree if and only if there exists a cut such that the edge is the minimum edge which goes over the cut. And so how can we do this in this setting? So in this setting, I'm saying, so look at the Delaunay triangulation. So I call it dt at most E of P. And so what do I mean by this? So this is the Delaunay triangulation. But these are all edges of the Delaunay triangulation whose length is, oh, let me write it like this, whose length is strictly less than E. So we look at the Delaunay triangulation of E, but not all, so I look at the subgraph of the Delaunay triangulation of P, consisting of all the edges that have length less than E. So this is subgraph with short edges, with edges and now I know that this edge E here is part of the minimum spanning tree, of the Euclidean minimum spanning tree, if and only if it goes between two connected components. Yes? So E is EMST of P if it belongs, if it goes between two components of dt at most E of P. Yes, you all believe this? So I mean there's two possibilities. So now I look at the subgraph and there's two possibilities. So either it looks like this, and in this case it's E is part of the minimum spanning tree, or it looks like that. In this case, it's not part of the minimum spanning tree. But now the question is, how does this help? I mean, so now we have some characterization in terms of connected components, but still we cannot. And okay, it's also possible for us to find all the edges of this graph. So I mean, we can find this graph because we can just enumerate all the edges of the delinear triangulation and look at all the edges which are and filter out all the edges which are shorter than E. So this is fine. But then how do I find the connected components of this graph? So I can't really do this because I don't know how to do breadth-first search. So it seems like this does not really help. Or does it? And so how do we continue? What do we do with this? And now the idea is, so what do we use? Now we really need to use all the power of what we found out. I mean, it's so we really need to use everything which we know now. And so the thing is, so we look at this picture. And even though we cannot compute the connected component, I mean, this picture is really authentic, right? Because, I mean, usually you draw these things in graphs, but the graph may be much more complicated. But we know that we're talking about some specific graph. We talk about some subgraph of the delinear triangulation. We know this graph will be a planar graph. So it will be embedded in the plane. So this actually is something which lies in the plane. And what I can do is I can try to start walking. So I know P. And I have some algorithm how I can enumerate all the edges. So I can use my algorithm to walk from P along the face which contains P, right? I can walk. I walk. And then there are two things that can happen. So what I'm doing here is I always use my new algorithm for finding the next denominator edge, like this. And so this I can use, well, and I use it in a way such that I filter out the edges which are, so that I can filter out the edges which are less than E. And so this allows me to walk along this face which contains P of this subgraph of the delinear triangulation. And then two things can happen. Either I end up at P again, and this means this is one connected component. So if I walk and I find P again, so I walk in a circle and nothing happens, then I know this edge here will go between two connected components and it will belong to my Euclidean minimum spanning tree. Or I start walking from P like this, but I meet Q along the way. And if I meet Q, I know that the edge goes inside this connected component. It connects two parts which belong to the connected components. And this means the edge is not part of my Euclidean minimum spanning tree.
So is it possible that there are two paths, one of them is from P to P and one other is from P to Q and then P?
So you're saying, may it happen that that P appears several times on this face? So
when you find it.
Yes. So let's see. So maybe I need to be a bit more careful in what I'm saying. Certainly what is true, so if you walk for n steps, and after n steps you do not see Q, then you will never see Q. Or 2n steps, so but some linear number of steps. This is certainly true. But I'm thinking, yes, it may be possible that this happens, right? So it may be maybe a situation like this, where here you have P, and here you have, so, and you
have two cycles in each other.
Yeah, so you're right. So I think this cannot be excluded. I think it may happen. So you're right. So I was too optimistic here. So it's not true that once you meet P, then you have to. So when you see P for the second time, it means that you have to stop. So this is probably not true. But certainly, what is true, you know that after n steps or 2n steps or some linear number in n steps. Let's see, maybe. Certainly 6n. If after 6n steps you don't see Q, then you will never see Q, and you're done. Yes.
When you find an edge that's in the triangle that the size is lower than E, then you will choose it. So you don't know. Maybe you trap in a cycle.
No, I know that I come with one edge. I come in with one edge which is larger than E, which is less than E. Right? I know that I come in with an edge which is shorter than E. And so I know that certainly my cycle will stop. Right? So what may happen is this, right? So it may be that I come from here, I come along this edge, and then there are all these edges here, but they are all too long, like this. And then I get back to this point. But then, in some way, I made progress, right? Because now I move in that direction.
And what if there are two edges that are shorter than you? You choose randomly one of them?
No, I continue along this edge, right? So I come from here, and I continue like this. But so the important thing is I stay on the outer boundary. So the idea is that I walk along the outer face. So maybe this picture is too simplistic. So in reality, it looks something like this, right? So the real picture would be probably something. So here I have P. So here's my candidate edge Q, and then there are some other edges, but it may look like. So it may be a tree, or there may be something inside. So you don't really know how it looks like. So it may be something like this, right? So this would be maybe a more realistic picture of how it looks like. And then I would go like this, I would go like this, then I would go like this, then I would go here, then I would go here, 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 and then I meet P again, and I made too many steps, or I see this edge again, and then it's over. Right? This is how it works. Yes? You all believe this? Everybody has some idea of how it works? Yes? And so this very much uses the structure of the Euclidean minimum spanning tree and of the linear triangle. So here I would say this is the first example where you really have to work. I mean, it's not too difficult yet. I mean, it's something which I could comfortably explain in 20 minutes or maybe a bit longer with the preparation, but still it's something different from what we usually do. So here you have to start to think differently in order to get something to work in the bounded workspace model, because the things which I used to before, they don't work anymore. Right? Or, I mean, but the ideas, of course, they're still there, the structure is still the same, but you need to do something else. Right? So this is maybe the first really interesting example. Okay, and so for the running time, so let's see, so how long does this take? So the analysis, so what is the running time? Let me see. So the running time is, so we have n edges. Okay, and so first of all, to find an edge of the, to find an or O of n edges in the Delaunay triangulation. And so finding an edge takes linear time. So to compute the edge, it takes linear time. And then we need to check the edge. And how long does checking take? So for checking, we need to walk. And when we walk, we look at most O of n edges. And we look at, and for each edge, so finding the next edge always takes linear time. So when we walk for O of n steps. And every step takes linear time, so we spend O of n squared time checking time per edge. Yeah, so now this is worse. So the time to check an edge is not O of n, but O of n squared, because I need to walk for n steps, but every step already takes O of n time. Or more. So this means the total running time is O of n cube. Right? So it's worse. And so I don't know if you can do better. I mean, it's a non-trivial algorithm, and the running time is not n cube, not n squared, as for dynamic triangulations, but n cube. So it's worse. And I have no idea whether you can do. So I'm not sure. So this was published maybe 5 years ago, or 4 years ago, something like this, depending on whether the conference or the journal version. And so this, as far as I know, has not been improved. At least I haven't seen anything. So yeah, I don't know if this can be done faster or not. Would be an interesting question. Okay, so this is it. So my time is over. I mean, I'm already, at least so I finished talking for an hour. And yeah, so that's it for today. So these are the simple algorithms. So tomorrow I will show you maybe one more simple algorithm, and we can, and maybe one more advanced algorithm I will sketch, and then I will start talking about time-space trade-offs. So here, up to now, we always looked at the case that we have constant space, but then the next thing I wanted to look at is what happens when you allow more space. How can you get some smooth trade-off between the running time and the space we're allowed to use? Okay, thank you.